what I'm interested in is studying the evolution of galaxies. That evolution involves feedback, which usually involves ejection of material. That's going to influence the cluster in which a galaxy resides, but also the fact that the galaxy is in a cluster is going to influence the morphology of the galaxy. So there's this interplay from the galaxy to the cluster and the cluster to the galaxy, which we would like to model in a unified way. First, let me give credits to people who did the hard work. This is a collaboration between people who are or used to be at the University of Washington in what we call the M-Body shop, and people at the University of Illinois, Sanjay Kalle's parallel programming lab that enabled us to do these large-scale computations. And there's others that I didn't have room to put their names on the slide, so apologies there. So a quick outline of what I'm going to talk about. I'm going to quickly cover scientific background. There's a lot of cosmologists already in the room. And then explain why, the need for high resolution. I had a previous PRAC which leads up to what I'm going to talk about today, so I'm going to explain some accomplishments from that PRAC, and then dive into the clustering issue and its specific computational challenges, how we address this these challenges with software on blue waters, and then finally talk about some of the accomplishments. Right, so the basic problem, how do you make one of these? So Brian set the context for this, that what you see here is not the complete galaxy. Right, this is buried in a much larger dark matter halo, but what you see here is quite important, and that is what you see is the baryonic physics. Specifically, stars are producing the light. The stars are also producing ionizing radiation, which is causing these H2 regions. The stars are also producing dust, which is causing these dark lanes. So all that you see here is the baryons, and so in that sense, even though the baryons aren't a large fraction of the galaxy, they are extremely important. And of course, you and I are made of baryons. The material that makes us today ultimately went through stars. And so for that case, for that instance, this is extremely important work. Again, let me reiterate the context. If this is the size of the galaxy, this is the size of the dark matter halo that it forms in. And furthermore, that dark matter halo is embedded in a cosmic web. Modeling the cosmic web is important because it's the torques from that web which causes the spin of the galaxy. And of course, the material from the galaxy flows in from that web. So that gives you an idea of the range of scales. And the real issue here is, as I explained, everything is going through stars. And frankly, we just don't understand star formation because of all the physics that's involved. You have the basic gravitational instabilities. We understand Newton, but it's hard to calculate. And then there's all this other physics that goes in sort of locally, but this is also happening in a turbulent medium where the turbulence is being driven on large scales by the differential rotation of the galaxy. It's also being driven at small scales by supernova going off and stellar winds. And all this stuff is happening on scales that, at least for the moment, we can't hope to resolve in a cosmological simulation. So what do? Well, we hide all that here's sort of pictorially what the problem is. The key thing is that this is 4 parsec scales. This is a picture of the molecular gas in a star-forming region. 4 parsecs, we're trying to model kiloparsecs to megaparsecs to hundreds of megaparsecs. How could we possibly resolve that? Well, we resolve that with subgrid models. We need to capture the large scale I just mentioned. For the small scales, we're putting this into a model where we do have the stars form in high density environments. That is, we're looking at scales of molecular cloud size, so 10 to the 5, 10 to the 6 solar masses, and we can get those properties in our cosmological simulation and use that as a star forming model, and then model the subsequent supernova feedback that regulates the star formation, preventing all the baryons in the galaxy from turning into stars. We have to mitigate issues with overcooling, and we run a number of simulations to model present-day galaxies, which we use to tune the star formation parameters. So that sort of sets our model, and once we set it, we can start making predictions about, say, galaxies in different environments. So with the previous PRAC, I think we were successful. We can, okay, this is not as high resolution as the observational picture I showed you. Nevertheless, we're getting galaxies with good spiral morphology. We're getting reasonable star formation histories. We're getting reasonable conversion of baryons into stars as a function of halo mass. We're getting these morphologies across time. Note here, right, blue is young stars, red is old stars. So we're seeing the decrease in star formation rates over the age of the universe as is observed. However, we were having troubles with large galaxies. So supernova are energetic, but they're not quite energetic enough to suppress star formation in the centers of large galaxies. By large, larger than Milky Way sized galaxies. So to address that problem, well, we know there are supermassive black holes in the centers of galaxies. We model the feedback from those black holes. We introduce black holes where they form from dense, low metallicity gas. Brian explained this in his talk a couple days ago. So similar idea of what he was modeling. And then the black holes accrete gas. As they accrete, they're messy eaters, so a significant fraction of the accreted gas gets turned into energy, and that provides the feedback to regulate star formation in the centers of the large galaxies. And then, since we model the individual black hole formation, we can follow the dynamical friction as these black holes sink to the center of merged galaxies, and we can make predictions for future gravitational wave experiments. So that's all terrific. This is with the black hole feedback. This is showing how we can get the observed stellar mass to halo mass relationship as a function of the halo mass. The observed is the red line. Blue points are from our simulation, nicely following this even up to 10 to the 13 solar masses, so small groups of galaxies getting this correct. So this is all wonderful. I want to make a point. Well, we can also get the black hole stellar mass relationship, which is terrific. I wanted to make a point about, Tiziana brought up the need for legacy preservation of simulations. We talk about disk repository. And this is an example of science that came out that was not part of the original simulation. And in this particular science is direct dark matter detection experiments. So we want to know, if I have a dark matter direct detection experiment around a star in a solar-like orbit in a Milky Way type galaxy, what would the dark matter signal be in terms of the velocity distribution function? Well, we did this simulation. We have a collection of roughly a dozen or more Milky Way type galaxies, which we can perform that experiment and make a model signal that we can compare with direct dark matter detection experiments. This particular experiment is on the University of Washington campus. It's looking for axions. So axions is said to be the thinking person's dark matter. Well, I mean, it's very, highly motivated because it also solves this strong CP problem in particle physics. So we applied this model, we, meaning somebody else, not me, to data from the axion dark matter experiment. And the latest results just a month ago showing that, so this is a range of axion mass, and this is predicted coupling constants. The lines are two minimal coupling models, one where it couples only to hadrons, the other where it couples both to leptons and hadrons. And so the experiment has been able to rule out a certain mass of axions as a potential dark matter candidate with the help of our simulations. And so this sort of exaggerates it. What it essentially does is, by a better signal model, we can reduce the signal to noise of the experiment by a factor of about 50%, but that's real money for since you're running an experiment. So this is a wonderful result that I originally didn't plan to have come out of our simulation. Okay, I need to move on to clusters. I don't need to really tell you how important they are. A key point I want to point out is that the baryon content is kind of hard to see in galaxies, but it's obvious in clusters. So the pink you see here is X-ray image. And so most of the baryons are seen in the X-rays in this pink image. And of course, the rest of them of the baryons are in the galaxies. And the other thing is, right, we drop the galaxy into this cluster, and all the material in the galaxy stays in the cluster. And so we have this closed box in which we can study galaxy evolution. But it has a challenge. I told you, we have to resolve the star formation if we want to study galaxies, but our clusters are much bigger than galaxies. So instead of going to 10 to the 12 solar mass objects, now we're going up to 10 to the 15 solar mass objects. And then the other challenge is that we need to do all the calculation where the cluster is, and that means that the calculation is clustered on the computer as well. And so having software that can distribute the load in an efficient manner is very important. So we've built this code. We call it Changa for Charm N-Body Gravity Solver. It's got all this physics in it, but it's based on this Charm++ runtime system. The advantage in particular is that it can manage moving the work to available processors, well, with a little bit of hint from me, but mostly automatically. And that's allowed us to scale to not quite the full machine, but 500,000 cores. And this is with a cluster simulation. So this 90% scaling is for a simulation that looks like this, where you have this, well, this is a small group up in the corner that contains perhaps 1/100th of the mass of the entire simulation, and it's still able to scale well.
Is this the whole simulation box?
This is a slice of the simulation. So the width is a whole simulation box. The maybe a 20th thick. So there's these, well, in the interest of time, let's just show this visually. If you look at the computational load on a large simulation, all the computation is being done in the center. We have to, each point on here is actually a virtual processor showing the load. And we're able to use Charm++ to distribute that load across blue waters. So, quick summary of results. Let me just go through it. It is one of the highest resolution simulations of a cluster to date. Here's a very surprising result. This is looking at the brightest cluster galaxy in the middle. And we're able to get these collimated outflows of thousands of kilometers per second. The surprise is that our feedback is not directional. We're putting feedback in as thermal isotropic feedback from the black hole. The material in the galaxy, or actually I don't know why this is happening, but it is forming these columnar flows into the surrounding regions of the cluster, evacuating these cavities around the central cluster galaxies. These flows are happening across cosmic time, and the flows are quenching the star formation. So we have the blue is the star formation, the red is the black hole activity, and notice the correlation. As soon as the black hole activity spikes, the star formation cuts, and that happens all the way across time until we get to the end, and where star formation shuts down entirely, and we get a red and dead galaxy in the middle of our simulation. The galaxy fits on the stellar mass halo mass relation. The morphology, well, this is not M87, so little issue with the morphology. One interesting thing has happened at this, a recent merger obviously has disturbed this galaxy. So that's why it's not looking so smooth. Star formation's being quenched. We're seeing that the quenching is happening for the large galaxies as they approach the center of the galaxy. So don't have time. It seems like ram pressure is the main quenching mechanism as galaxies fall into this cluster. The Intra Cluster Medium fits on the observed relationships, that is entropy temperature diagrams. So that's wonderful. And then finally, a couple takeaways. Although galaxies are hard, and we still haven't included all the physics necessary, thank you, but it's now doable, mainly thanks to blue waters, but also Charm++ type software that's able to scale our code efficiently across the machine. And so I think indeed we have the first holistic simulations of galaxy clusters. And if you're interested in more, this morning's Astro PH, it's the third one on the new articles this morning. So this is hot off the press.